This is the 41st video supplement for CIS 351, Grand Valley State University's course on computer organization and assembly language. This is the third of 3 videos that discusses how to call functions in assembly. This video demonstrates how to properly save data before calling a function so that it isn't overwritten. The previous 2 videos examine the assembly version of this code, which determines which of 2 prices is closer to a target price. We saw in the previous video that failing to coordinate register usage between functions leads to registers getting clobbered, which in turn leads to infinite loops or incorrect output. We ended that video by asking how you avoid conflicts between functions over registers. The first thing to understand is that the solution needs to be automated. It would be tedious and inefficient to make the programmer explicitly look up and avoid all the registers used by any of the functions that need to be called. Such a requirement would also be bad from a software engineering standpoint because the functions would be too tightly coupled. By this, I mean changes to one function could potentially break the other. In our running example, the person in charge of maintaining the absolute value function should be free to modify that code without fear of breaking the functions that call it. And to be clear, I'm talking specifically about internal modifications. The function still has to honor its interface by returning the absolute value of its parameter. Of course, if you change that, then code that's relying on the absolute value is not going to work. But changing implementation details, such as the registers used locally inside the function, shouldn't affect any of the functions calling it. Trying to coordinate register usage gets even more complicated when you realize that you have to consider not only the functions called directly, but all functions in the call stack. In the diagram to the right, function B must not only worry about conflicts with functions C and D, but also with functions directly or indirectly called by C and D. Anything shown in green in the diagram. So as a practical matter, you have to assume that any function you call might change the values in any of the T registers. So if you need to make sure a value is preserved while another function runs, you have to move it out of the T registers to somewhere safe. So where is a safe space that you can put data so that other functions won't mess with it? Well, for reasons we've just seen, that safe space isn't going to be any of the registers. First, trying to coordinate registers will just get complicated in a hurry. Plus, most programs have a deep enough call stack that 32 registers simply won't be enough space. So if the registers won't work, the only other place we've discussed that can store the data is RAM. So in principle, when you call a function, any data that needs to be preserved, that is, any data you'll still need after the function returns, must be saved in RAM. So first I'm going to show you a direct but inefficient technique. And then I'll show you a common optimization. The challenge when storing this data in RAM is keeping track of it all. How do we organize where we put all this data? One idea, based on a recent video, is to create a label for each local variable that needs to be saved. But do you see any problems with this? Well, I see 2. First, it would use too much memory. Remember, only a few functions are active at any given time. For example, while function I is running, we need only store the local data for functions above it in the call stack, the functions shown here in green. Functions to the left, like B and H, are complete, so their data is no longer needed. Functions to the right haven't been called yet, so there's no data to store. In both cases, we want to avoid tying up space in memory that just simply isn't being used at the moment. Second, this approach won't support recursion. If a method called itself recursively, that recursive call would overwrite the local data from the calling method. To address these limitations, it's best to wait and not reserve space in RAM until a function's actually called. If we do this, if we only reserve space as each method is called, and lay that space out in order, then that data stacks up. That's why we call it a stack. So the stack is just one portion of user data. We add data in a last in, first out order, just like the stack data structure. When a function's called, we push that function's data onto the stack, and we pop it off when the function returns. As a result, only data from functions that are currently in progress are stored in memory. And since every time a method is called, it puts additional data on the stack, this system supports recursion. Each time a method calls itself, that additional invocation gets a separate space in memory to hold that local data. So let's walk through an example. We begin by putting the last address of our data space in register SP. SP stands for stack pointer. And in MIPS, the stack pointer points to the location of the last item placed on the stack. So suppose your main function needs to store 12 bytes. For example, suppose that there are 3 integers that you need to save while another function runs. So to save those integers, we subtract 12 from the stack pointer. This has the effect of reserving 12 bytes of data that nobody other than the main function is going to use. Main then accesses those local integers using the stack pointer with offsets of 0, 4, and 8. Now, suppose main calls method A, and method A needs to store 16 bytes of data, for example, 4 integers. As before, we subtract 16 bytes from the stack pointer, which reserves 16 bytes of data on the stack for the exclusive use of method A. And now method A can access its local data using the stack pointer with offsets of 0, 4, 8, and 12. Notice that we're able to provide space for both methods on the fly without having to statically allocate space for all those local variables in advance. Now, if method A called a function, we just push the stack pointer down again. And if that function called another function, we'd push it down again and again and again and again as that call stack got deeper. Now, at some point, those functions will all return. And so when it's time for method A to return as well, we add 16 bytes to the stack pointer, which implicitly frees that space and makes it available to be used by the next function call. For example, when main calls method B's local data goes in the space vacated by method A. So this is how we can efficiently store all of that local data on the stack without leaving holes for methods that aren't running. And notice how it also provides an easy way to find the data we need without having to create a whole bunch of labels. So let's see how to apply this technique to our running example. So remember, we have 2 functions, the first one being closest price, which determines which of 2 prices is closer to some target, either above or below, and the absolute value function, which just returns the absolute value of its parameter. So as written here, this code has a couple of problems. So remember from a couple of videos ago, the return address was getting overwritten. And also, we had a conflict with register T0, where closest price and absolute value were trying to use the same register to store data at the same time. So let's see how we could use the stack to clean it up. Now keep in mind, what I'm going to show you first is not the technique you'll find in the textbook. I want to illustrate some of the key principles first, and then we'll see how to optimize it a little bit. So first, let's look at closest price here. So we see that we take the parameters and we save them in registers so we can use A0, A1, A2 again. And then we subtract A from the target and call absolute value. And then we save that return value. Then we subtract B from the target and call absolute value. And then we compare those 2 absolute values. So the first question we want to ask is, what data needs to be preserved while the absolute value functions are running? So let's see. At the end of the function, we either return price A or price B in T0 and T1, so both of those need to be saved. And across the second call to absolute value, we have to remember the absolute value of the difference between price A and the target. So that T3 register needs to be saved, and the return address needs to be saved. So there are 4 integers that we will need to save on the stack. So the first thing we'll do when we enter this function is make room for those 4 integers on the stack by subtracting 16 from the stack pointer. And the first thing we'll need to save is that return address. So I will save that memory location right at the stack pointer. And so we don't need this anymore. I also know that I'm going to need to save T0 and T1. So I will save T0 at an offset of 4 from the stack pointer and T1 at an offset of 8 from the stack pointer. So now when I call absolute value here, I don't have to worry about the return address getting overwritten. I've saved it in a safe place. I don't have to worry about T0 or T1 getting overwritten, right? It doesn't matter which register's absolute value uses because the values I'll need later I've put in a safe space. So now after the first call from absolute value returns, I need to save that value so it doesn't get clobbered by the second call to absolute value. So again, I'll put that in some space I saved on the stack. Now notice earlier, I took that return value and saved it in T3. Well, we don't really need to do that. We can just save it right on the stack. No reason to take 2 steps to do that. So we'll put V0 in 12 plus the stack pointer. So now we go and make our other call to absolute value to find the absolute value of the difference between the target and price B. And so when that comes back, now I need that original difference, that one up here from the first call. So I will retrieve that from the stack. And now I'll put it in T3. And I'll do that comparison. And we've got our branch if equal. And now here's where we had the problem in the last video, where T0 got overwritten. So instead of grabbing that value from T0, I will grab it off the stack. And then the next step is to return from the function. But this time we have a little bit of work to do. We have to clean up our stack. And notice we'll have to do the same thing down here. So I'm going to consolidate that rather than cleaning up the stack twice in 2 different places. I'm just going to do a jump to return price. I'll make that a new label. So we'll replace this move with an analogous call. We'll set up V0 to have price B, which is stored at 8 plus the stack pointer. And now we'll set things up to return. First, we need to get our return address off the stack, which we placed right at the stack pointer. And we need to restore the stack. So before we return from the function, we need to put the stack pointer back where it was when we started. And we do that by offsetting the -16 with a +16. And now we can do our jump register to return. So now let's see what happens when we run the code. So we'll step through one line at a time. So we get to the end, and we look in V0, and we have the value 9, which is the correct answer. So we did fix the bugs. But actually, it turns out we just got lucky, because I forgot a local variable. If you look here, we need the value of T2, that's our target price, after we return from the first call to absolute value. So we got lucky because absolute value doesn't happen to use T2. I left that mistake here in the video just to show you how easy it is to make. Right? One of the main challenges with assembly code is not using the instructions and using the branches and the jumps and all of that, but keeping track of all the stuff by hand that you need to keep track of, like setting up the stack, getting the right values on the stack, tearing down the stack, and so on. There's a reason we prefer languages like Java and C to writing in assembly. Now, I mentioned at the beginning that although this technique works, it's not exactly what the textbook is going to show you to do. And the reason is that it's just slightly inefficient. So if you look here, we got into the middle of what we were doing, and we had to retrieve data off the stack in the middle of the function. We needed that value of T3 back. So it's not terrible, but it would be nice if we could consolidate all of our stack stuff in one spot. And although this code doesn't show it, imagine if any of these local variables, T0, T1, T2, changed frequently during this code, then we would have to save them to the stack before every call to absolute value. So if there was some work done in here that changed T0, T1, and T2, then I would have to take time to save those to the stack before I called absolute value again. So in a function with many function calls and many variables, you might spend a lot of time explicitly pushing that data to and from the stack before and after each function call. So not only does that clutter up the code a bit and make it hard to read, you're also making more accesses to memory than you really need to make. So I'm going to show you how the textbook suggests you organize your code, which makes it a little bit cleaner and cuts down on memory accesses a little bit. Okay, first look off to the right at the names of all the registers. Most of these we've talked about before: the 0 register, the assembler temporary register. So we have our V registers and A registers for parameters and return values, the T registers, and then we come to these S registers that I haven't said a whole lot about. But notice here on the tooltip what it says. It says save temporary, preserved across call. So here's the idea. We take our workhorse registers, the T registers and the S registers, and we divide them into two groups. T stands for temporary, and as I mentioned earlier, those registers are free for all, so you don't expect data left in a T register when you call a function to be there when you come back. The S stands for saved. So by convention, when you put data in an S register, functions you call shouldn't mess with it. So what we'll do is we'll take data that we need saved across function calls and put it in an S register instead of a T register. So for example, when we save the parameters, the values of A, B, and the target, we'll put those in the S register. And when it comes time to save that value of V0 that comes back from the first call to absolute value, we'll put that in an S register as well. And now we'll change the rest of the code. So for example, we've got S2 instead of T2 here, and S1 instead of T1 here. Now, because we put that return value from the first call to absolute value in an S register, and we're assuming that it doesn't get messed with, we don't need to retrieve this value from the stack anymore. We just refer to S3. Now notice here, when we do this set less than, we're going to still use the T register here because the return value from this set less than gets used in the very next instruction, and that's all we need it for. And now again down here, we don't have to grab the data off the stack. We can just go back to taking it out of the S register. And here as well. So that seems kind of nice. Use the S registers, functions you call don't mess with it, and we don't have to worry about the stack or anything, right? Well, wait, that doesn't seem right. Just using S registers can't magically solve our problem. What are we missing here? Well, think about it. The convention is that functions don't mess with the S registers. That's what allows us to assume that absolute value is not messing with S0, S1, and S2. But wait, if we're using S0, S1, and S2, what about whatever function called closest price? Maybe it used an S register and it's expecting us not to mess with it. Well, that's true, so we have to account for that. So if you're going to use an S register, you're responsible for putting it back the way you found it, so that whatever function calls you can't tell that you've touched the S registers. So we still need to use the stack. It's just that we've limited the access to the stack to the very beginning and end of the function instead of having to spread it throughout the code like we did in the previous example. So let's see what we have here. We used 4 S registers, S0, S1, S2, and S3, and we still have to save our return address. So I mentioned I goofed in the last example. We actually need 20 bytes of data on the stack. So we'll begin by putting that return address on the stack where it's safe. And since we want to use registers S0 through S3, we also have to save them so we can put them back the way we found them. And now we can make use of them. We don't need this access to the stack anymore. We have our much more straightforward code here without having to take a break to deal with the stack. And then at the very end, right before we return from the function, then we need to put everything back. And that includes the S registers. We also have to return the stack pointer the way we found it, and we're good to go. So again, let's make sure this code runs correctly. So we'll step through. We get to the end. We have a 9 in V0, so it looks good. So like I said, there's a couple of benefits here. One is organizational. It's just a little easier to keep track of what you're doing when you have just some stack setup code at the beginning, some stack cleanup code at the end, and then you don't have to worry about it in the middle. The other potential benefit is spending less time moving stuff on and off the stack. Because a function that doesn't use any saved registers doesn't have to bother cleaning and restoring the stack. So closest price, because it does need the S registers, has to preemptively save all of those S registers on the stack because it has no way of knowing if they're in use. But after setting up the stack with those S registers, it doesn't have to move stuff on and off again like it might before and after each function call. It just has to do it once during the function, which is helpful because you don't really know which function calls are going to potentially mess with those registers and which ones don't. So rather than you saving everything every time you make a function call, just let the function you call, like absolute value, move what it needs to move, which in this case is nothing. It only needs T registers because it's what we call a leaf function. It itself doesn't make any additional function calls. MIPS divides its registers into two categories: preserved and non-preserved. The S registers, the return address register, and the stack pointer are all classified as preserved. That means if you use them, you're expected to put them back the way you found them. Or in other words, clean up after yourself. The T, A, and V registers are all non-preserved. That means you can use them whenever you like, you don't have to worry about what's already there, and you just forget about them when you're done. However, that also means when you call a function, you have to assume that the values in these registers have been changed. The main way to keep this straight is to remember that T stands for temporary and S stands for saved. Use an S register when you need to save data across function calls, and use a T register to store temporary data just between a few instructions. So here's the general process for preserving data across function calls. First, you need to look through your code and figure out how many bytes of data you're going to need to save, how many S registers you need. And then, at the beginning of the function, you need to subtract that number of bytes from the stack pointer. That makes room on the stack. It reserves a piece of the stack that nobody else is going to touch. And once you have that piece of the stack reserved, take the data you're responsible for cleaning up and save it on the stack. So if you want to use an S register, because you're responsible for restoring that S register, you have to take the data that's there and put a copy of it somewhere safe. That safe place is the stack. Then your function can go about its business, and then when it's time to exit the function, you need to clean up. So you take that data that's been safely stored on the stack and put it back in the registers. Then you also have to restore the stack pointer to the value it had when it entered the function. And so you just have to remember how much you subtracted from the stack pointer, and then you can add that value back. The important thing is all the preserved registers should have the same values before and after a function call. So this is kind of cheesy, but if you have a party, the house has to be just as clean when your parents come back as when they left, so they can't tell you had a party. Well, with the possible exception of your T registers, right? Maybe you look in the garbage can and there's garbage there, so something happened while they were gone. But the important parts of the house have to be cleaned. Just like the important registers, the preserved registers have to be restored, whereas your temporary or trash registers can have whatever left over in them. Now let me point out that when you're writing assembly code, especially more complicated assembly code that uses several functions, if you get really weird behavior, your problem is probably somewhere in this process of preserving and restoring registers. Now assembly itself will lend itself to weird errors popping up just because it's so low level. But if you're getting a bug that kind of feels like a bug you'd get in C or Java, it's probably a logical error in your code itself. But if just really weird stuff is coming out of nowhere, you've probably goofed up the stack somehow. Either put something in the wrong spot on the stack, or you didn't correctly return the stack pointer to its original position, meaning the calling function is no longer looking at the data it thinks it's looking at. All right, so let's take one last look at this process here in the context of our running example. So with closest price, we first had to go through and see how many variables we needed to save across the calls to absolute value. And we figured out we needed to save 4 integer variables. You also have to preserve the return address. So that gives us 5 integers we have to preserve while running this function. 5 integers at 4 bytes an integer is 20 bytes. So we begin by subtracting 20 from the stack pointer. We then preserve the values of the return address register and 4 S registers by copying that data to the stack. Once it's on the stack, nobody else should be messing with it, and then we're free to use the return address or the saved registers as necessary as we go about the ordinary business of calculating the closest price. And then at the very end, before we return from that function, we have to put the preserved registers back the way we found them. And we do that by loading the data back from the stack into those registers. Once that data is loaded, we free that space on the stack by moving the stack pointer back up 20 bytes to its original position, and then we can execute the jump register instruction to leave the function. Let me point out that with earlier assignments, you probably had multiple return statements, multiple places that a function could exit using that jump register instruction. Once you get into a function where you have to save and restore the stack, then it's often convenient to jump to a single location so you don't have multiple copies of that code throughout the function. Oh, and I almost forgot. If you ever have a function that needs more than 4 parameters, you pass the values on the stack. Almost forgot that part. Okay, so this has been quite a long video. I appreciate your endurance in watching the whole thing. The next video will talk about system calls.